Welcome to a brief introduction to the principles governing mass spectrometry. I'm going to show you a very basic mass spectrometry experiment and how these instruments function, keeping in mind that there are many different ways to accomplish the goals that I'm about to show you. Now, there are three basic steps in a mass spectrometry experiment. The first step is to ionize the compounds we'll be analyzing. They need to be charged in some way. In this example, we'll be using these red or pink colored spheres to represent molecules that we'll be analyzing. And we need to turn those into charged species so that we can conduct the mass spectrometry experiment. Once we've created our ions, the next step is mass filtration or mass analysis. In some way, we need to organize all of the ions generated based upon their mass and separate them in space because of this parameter. The final step is detection. In the detection step of the experiment, we'll be trying to locate where and how these ions are moving and use that information to determine what their masses must be. This is the source of mass spectrometry experimental data. Let's begin by considering how to ionize a molecule. And I'll be showing you today one of the most basic but most widely used ionization methods in mass spectrometry. That is electron impact ionization. In electron impact ionization, the gas phase molecules are passed through an arcing electrical current, which consists of very high energy electrons. On occasion, one of these high energy electrons will strike the molecule, creating a radical cation by knocking a second electron out of the outer shell of that molecule as it passes by. Now let's take a look at the top left of this slide and watch our first example of what can occur when a high energy electron strikes a gas phase molecule. When impact occurs, a second electron is knocked out, almost like a billiard ball. And the result of this is a radical cation, which has lost a nominal amount of mass. It weighs essentially exactly the same as the molecule itself did, minus, of course, the weight of an electron. But this is not always the case. In some instances, when an impact occurs, not only is the molecule ionized, but the radical cation fragments in such a way that frequently the radical goes to one side of the fragment, whereas the charge goes to the other side. In the depiction I've just shown you, the larger of the two fragments is the one that receives the charge. This is, however, not necessarily so. It's entirely possible that when the cation is formed, that instead the charge is carried by the smaller fragment. So as you can see, there are a number of different ways that these ions can be generated, each of which creates an ion of a different mass. And we should keep in mind that this process is not necessarily going on one molecule at a time. We're looking at a large assembly of molecules. And so really what's going on inside the ionizer is many impacts are occurring, generating many different ions and fragments. And so we have to deal with this large collection of ions of different sizes. Now that we've created our ions, let's move on to the mass filtration or mass analysis step. In this step, the ions which are formed are focused into a beam. If these beams are focused into an area in which there is no appreciable magnetic field, the ions will move in essentially a straight line. This doesn't help us very much to separate them in space. Therefore, we apply a magnetic field to the region through which this ion beam is moving. When we do this, the applied field causes the ions to experience a force. Recall from the right-hand rule of physics that a point charge moving at a given velocity through a magnetic field will experience a force, independent of the mass of that particle. Therefore, one could assume that the force acting on all of our ions, both molecular and fragments, is the same. Because force is equal to the mass times the acceleration of an object, we can calculate that the acceleration of any object must be equal to the force divided by its mass. In this instance, because force is constant for all ions, we can then determine that the acceleration is proportional to the reciprocal of the ion's mass. In other words, lighter ions will be deflected to a greater extent than heavier ions. This will cause them to be separated in space. As you can see in this example, the smaller green-colored ions are moving with a greater degree of curvature. and this means that they reach the bottom of the screen at a location closer to the source. So now that we have separated our ions in space, we need to bear the burden of detecting exactly where they have gone so that we can then back calculate their masses. One method of detection which is frequently used in mass spectrometry is the electron multiplier. An electron multiplier is a series of special plates known as dynodes, represented here by these gray colored bars. Now, dynodes are made of a material which ejects electrons in response to physical impacts, such as, for example, the impact of a cation or the impact of an electron. This means that if our analyte ion is moving into our detector and strikes a dynode, it's expected to then perturb this dynode in a way that causes the release of an electron, at least one, sometimes more. This electron traverses the electron multiplier assembly and strikes another dynode. Now in this case we're going to produce 3 electrons per impact. So our 3 electrons move to the next dynode where there's a new impact, which creates 3 more per electron for a total of 9. And then a new set of impacts creates even more. And very quickly, a measurable amount of current is generated. In our cartoon, we've only created about 20 or so electrons from a single impact, when in fact, within the instrument, about 1 million electrons are generated per impact in a well-tuned electron multiplier. This means that it only takes a few impacts to generate enough electrical current for the workstation computer to pick that up and read that as a signal coming from the detector. Now let's take a look at how all of these different elements can be combined into a single experiment which will tell us something about the mass of our compound. I'm going to begin by animating this schematic of a mass spectrometer. As a stream of gas phase molecules enters from the left-hand side of the slide, it reaches the ionizer, where the beam of molecular ions and fragment ions is generated. From this point, the stream of molecular ions then moves to the mass analyzer, where the ions are separated in space based upon their mass, or more accurately, on their mass-to-charge ratio. Notice that the ions within the mass analyzer are deflected to a different extent by the magnetic field, meaning each beam reaches the other end of the mass analyzer at a different position. If I place a detector in a fixed location near the end of the mass analyzer, in this instance, only those intermediate-sized ions are striking the detector. Because they are striking the electron multiplier, it's going to generate a current at this particular field strength and shape. Now let's take a look at the effect of altering the intensity or the shape of this magnetic field. If I increase the strength of the field, I increase the force acting on the ions, meaning that their path curves to a greater extent. In the example shown here, we've increased the field strength to the extent that the intermediate-sized ions no longer reach the detector, but the curvature of the molecular ions is not sufficiently steep, and so nothing is striking the detector at the moment, meaning that at this particular field setting, the detector will be silent. No current is generated. If we increase the field strength one more time, notice that now the molecular ions are striking the detector, which will generate a new current. So at this particular field strength, the computer workstation will know that there is some type of an ion which is reaching the detector. Creating a plot of the intensity versus m over z gives us our mass spectrum. What you're really looking at in a mass spectrum is not a plot of intensity versus m over z per se, but rather a plot of the amount of current which is exiting the electron multiplier as a function of the field setting. So the field setting will tell us what mass should be exiting at that time, and the electrical current generated by the detector will tell us whether or not any ions of that particular mass are present in the sample.